roll mark. That took a while. And we're now recording. I'll even turn on the projector in just a second. I'll go from current slide. Before we actually get going, I did find two things in the email that you might need to know about. If not you, someone you might know. I guess Mr. Jefferson is one of our coaches here. I don't know him personally, but he sent this email, and the subject is a job offer, and the company name is No Kid Hungry. The company description, No Kid Hungry, is working to end child hunger in America today by ensuring that all children get healthy food they need every day to thrive. The job title is Brand Ambassador, and that's all it says. I don't know what that means. The job description is send out the items through the mail to the list of orphanage homes that would be provided to you in your city, mailing out letters of invitation from us to other non-governmental organizations, NGOs, foundations, or businesses in your city. Interested candidates should contact Henry, that's strange, via email at HS, and there's the email here. So funny, it's just two initials, HS, and then a series of digits. For more information, the weekly wages, frankly, they sound fairly weak too, is $350, okay? Maybe that's good, I don't know. It just seems a little on the low side. Thank you, looking forward to hearing from you. It says Coach Jefferson, Washington State Community College. So if you know of anyone who's looking for, sounds like a very necessary job, a very rewarding job, except maybe, in fact, okay, but it doesn't have a deadline or anything else attached to it. It just came out. I'm sure it's still open. Now, this I saw posted on the Birmingham campus, but I haven't seen it posted here. Maybe it is somewhere, I just haven't seen it. But this is from the academic dean. It's the SGA, Student Government Association, Student Drive, Please Support. It's Lawson State faculty, staff, and students. Please contribute to this important SGA drive. Thank you. And it's sponsored by the Lawson State Student Government Association and the Ambassador Program. It's a personal hygiene drive. All donations will be distributed to local homeless shelters. Now, it says November 13th through the 22nd. I don't know if that's when they're picking them up or if that's when they're distributing them, okay? But they just sent this in the middle of this on the 19th. But like I said, I saw it on the wall on the Birmingham campus last Friday. Now here, okay, donation drop-off for the Birmingham campus, the Academic Success Building. You're familiar with that new building. Okay, it says on the Bessemer campus, Student Activity Recreation Center. I think I know where that is. That's right across from the cafeteria. I think a pool table or foosball or something in there. And I think that's the best I know for that. Well, I brought stuff in yesterday and went by twice to deliver, and both times the door was locked. So I went by to see if I could find someone who knew something. One of the first offices I got to was Dr. Renee Herndon, and she said, no, we don't have a student activities coordinator anymore for this campus. So therefore, as far as she knew, that room was being locked until they got somebody. So I don't know where to donate them. And I asked her about it. She said, well, I'll take them over to the Birmingham campus. And dumb me, I was thinking it was Thursday, not Tuesday. I said, well, I'm going tomorrow. I'll take it. I should have given them to her. But I may still give them to her today because I think they're still down there. But anyway, I don't know that there's a place on this campus to drop them off now. But here are recommended items. Shampoo and conditioner, soap, shower gel, combs, brushes, tampons and pads, lotions, deodorant, baby wipes, hand sanitizer, and socks. Okay? Now, they don't have anything about dental on the list, but they do have a toothbrush and toothpaste pictured here. So I had a spare thing of toothpaste at the house that hadn't been used, so it's still in the box, so I brought that. But, you know, a couple of other things, but those are the things you can do. Do you go to the Birmingham campus for? No, okay. I thought sometimes you're in honors college, aren't you?
Yeah, I go for that. They do one meeting on
every other.
Yeah, every other time.
Friday. Right? Are you here tomorrow? I mean Friday.
Yeah, it's on Bestford campus on Friday.
Okay. Yeah, well, I'm going to be taking some by Friday. If I don't go to Dr. Herman, then take over before. So, the deadline. I assume that that date is the deadline, November 22nd, which is sometime next week, isn't it? Tuesday?
I think so.
Okay. Because, nope, it's Friday. Friday is the deadline. So maybe I better give it to her today in case I forget to. All right. Yeah. So.
I had a quick question about the final.
Sure.
So, is it going to be on 9-1 and 9-2 and whatever we do in 10?
Yeah, 9-1, 9-2, whatever we do in 10, and if we get into 11, which I doubt, that's it. We're just going through these others, so you'll be, it's mostly for you because you're a math major, you might need these. Some of the others might also, I don't know, but you probably, more than others, would probably could possibly run into these that the others might not. So that's it. All right, I thought after all that, some more people might come in, but not yet. So let's get started. Any other questions? Okay, all right. Sorry about the board. I tried to see if I could erase it, but the eraser is smearing more than it's erasing. We got up to this, but didn't get this done last time. Again, you're not responsible for this for the test, but my fingers do better than the eraser does. This is the theorem that describes alternating series sets. Let A sub n be greater than 0. Okay, in other words, positive, no negatives. Well, you get negatives in that. The alternating series, the summation from n equal 1 to infinity of minus 1 to the n times a to the n, and summation of n equal 1 to infinity of minus 1 to the n plus 1 times a to the n. Now what this one does for you, all the odd ends are odd, okay, and all the even ends all the odd ends are negative, and all the even ends are positive. So when n is equal 1, that will be a minus 1. When n is equal 2, that will be a plus 1. N equal 3 minus 1. So a sub n is always positive. So whatever this coefficient is, that determines the sign. So here we have a series that the first term is negative, second positive, third, just go back and forth, positive and negative. This one, what happens, n plus 1, so when n is equal to 1, this will be 1 plus 1 is 2, so it starts off positive, and then goes negative. So this is positive, negative, positive, negative, positive, negative. This was negative, positive, negative, positive, negative, positive. Okay. Now, these two alternating series converge when these two conditions are met. The first is that the limit as n approaches infinity of a sub n is 0. That's all it takes. If it is a sub n as n is going to infinity is 0. Now remember, on a positive only sequence, like 1 over n, that will not converge. Okay? It will not. But 1 over n with one of these would. Because now you start out either positive or negative, and every one, and you're summing things, and the differences are getting smaller and smaller and smaller. So this will converge. That's all that's required is the limit for the sequence a sub n is 0. Okay? Now, here's the second condition. Okay? The a sub n minus 1 is always less than or equal to a sub n. Okay? For all n. Now, frankly, I can't see this being true without that being true. I just can't see it. I guess the only thing is they say maybe somewhere back here, a sub n could be greater than, but then the limit. But then it still seems like it would still converge. Maybe there is something subtle I'm not seeing there, but it seems like to me this would have to be true for that, especially for large n's. Now maybe not for smaller n's, but for large n's it would be, but that's what you're going to. For smaller n's, that's finite. Okay, they're done. Okay, so I can't see how the limit could be 0 if a subsequent one is larger than the previous one. It just, that would not go to 0. I guess you could do something. I don't know. Not going to ponder on it too long. Okay. All right. You think that's going to converge or not?
Yes.
Yes, because 1 over n goes to 0. Okay, so don't think there's any problem there. So it does. The first condition is satisfied. Also note the second condition is satisfied because 1 over n plus 1 is always less than 1 over n. Not even equal to, less than. Okay. So applying the alternating series test, you conclude it does converge. All right. The next theorem, there's a couple more examples, but okay. If you look at example 3b, I said maybe there could be some weird ones, and this looks like it's definitely a weird one. 2 over 1 minus 1 over 1 plus 2 over 2 minus 1/2 plus 2/3 minus 1/3. So I guess that does converge to 0. I can't see what the pattern is here. Yeah, I'm sure there is one. Yeah, the numerator is either 2 or 1, depending on whether it's the odd or even term. And then the denominator is the same for the first two, same for the next two, same for the next two, same for the next two. So the next one would be plus 2/5 minus 1/5, plus 3/5 plus 3/6, I guess. Yeah, minus 1/6. Plus 2/6 minus 1/6. Okay. It passes the first condition because as n goes to 0, that's ultimately going to 0. But because you're, let's see, if you notice there, the 1, 2, 3, 4, the fifth term is greater than the fourth term. The absolute value, the a sub n is greater, ignoring the sign. So that one doesn't. Now, it says so it diverges. They didn't say that before. They said converge when those two conditions are met. It may not, well, I guess it would either have to converge or not. Anyway, spent too long on that one. Now let's talk about the alternating series remainder. For a convenient convergent time, alternating series, the partial sums S of n can be a useful approximation for the sum S of the series. The error involved in using S approximately equal S of n is the remainder, which is R sub n is S minus S of n. So, here's the theorem, the alternating series, sorry, if a convergent alternating series satisfies that condition, that A sub n is less than A sub n, A sub n plus 1 is less than A sub n, then the absolute value of the remainder, R sub n, involved in approximating the sum S by the partial sum S of n is less than or equal to the first neglected term. Okay? So, if your S of n only goes to n, of course, the next term would be your A sub n minus 1. So your remainder, the absolute value of this, because this could be either positive or negative, because this could be a little bit greater than this or a little bit less than that. So the difference is you need absolute value bars. So you need absolute value bars here too, because this is always positive. And so if the remainder then would have to be less than or equal to that next term, the first neglected term out of that. So if you know what those terms are, just go to that term and then do your partial sums up to that term. Okay. Remember the sequence of the the individual terms have to be going to 0, but the series could be going to something else, okay, obviously, because it's a sum. Okay, so here's what we got, 1 over n factorial, which, by the way, even without alternating, that's going to be a convergent series, okay? But certainly with alternating it will. So it says approximate the sum of the following series by its first 6 terms. 1, 2, 3, 4, 5, 6. Okay? I'll just let them show you rather than we have to work it out ourselves. That would take too long. The series converges by the alternating series test because certainly this is less than that. Okay? And the limit of that is 0. Okay? So both conditions are met. The first 6 terms are this. And I'll just, if you haven't picked up on this, this denominator is 1, and 1 times 2, which is the next term, is 2, and the next term is 3, 2 times 3 is 6, the next term is 4, 6 times 4 is 24, the next term is 5, and that would be that, and the next term is 6, that would be that one. That's sort of an easy way to write this. You don't have to go back and do a factorial every time. The denominator being multiplied by whatever the next term the number of the next term. Okay. So you can punch that in a calculator, for instance, or anything else, and hopefully get something like 91 over 144. Glad we didn't have to do it, okay? That's approximately 0.63194, okay? Well, the question is, how good is that? How good is that answer? Well, what would be the next term? This was 6 times this, so the next is 7 times this. So, punch up a calculator.
5,040.
Okay, and then do a 1 over x, or x is minus 1.
0.0002.
0002. So this is good to almost that digit. Those first 3 digits for sure are good. The 9 may be good. So that's pretty good. I mean, that's more than most equipment can measure, okay? While alternating theory series test, that's the same thing you got, right? 50-40, okay? And then if you did that, that's 0.0002, okay? So the sum lies somewhere in between those differences, and frankly, I just can't see why they even have the 4 out there. The 4 is no good whatsoever. So it's between 0.6317, which is 2.0002 less, or 0.6321, which is 0.002 more. Those 4s, they're ridiculous to even have them there. If your precision can't be any more than 4 digits, then why even list the 5th digit? Okay? This, of course, is a math book, not a science book, so those are just completely useless digits to have that out there if your greatest precision is that, so don't even mess with those. Okay, that's just my gripe. All right, next subtopic is absolute and conditional convergence. Okay? Occasionally a series may have both positive and negative terms, but not be alternating. Alternating series, every other one changes sign. For instance, here's a series. Sin n over n squared. Okay? Strange series, but it's certainly fine. The numerator stays between plus and minus 1. But it can't be negative, right? The denominator is getting smaller and smaller and smaller. Okay? But it's not necessarily alternating the sign, because sine of 1, remember, in calculus, I want to say almost. I want to say always. I was going to say almost always, dealing strictly in radians, never in degrees. So this is sine of 1 radian. Well, sine of 1 radian that's close to 60 degrees. It's not 60, but it's close to it. So certainly that's positive. And then the second one, that's close to 120, that's positive also. But the third one, when you're down in the third quadrant, that goes to negative. Okay? The fourth one would probably be negative. And then, so it's plus, plus, minus, minus, plus, plus, minus. And then somewhere along the way you'll get off, because it's not quite up to 60 degrees, so at some point you'll have 3 positives or 3 negatives in a row, but then the rest will be always alternating into 2. So that's not an alternating series. Okay? Now, it has both positive and negative terms, yet it's not alternating. One way to obtain some information about the convergence of this series is to investigate the convergence of the absolute value of that series. Okay? Now, if you're summing up things that alternate plus and minus, and things are getting less, and these are pretty much guaranteed, not absolutely guaranteed to get less, because this denominator is going up really, really fast, so these numbers are getting very, very small. The reason you can't guarantee, you could be close to 0 in your numerator, closer to 0 than your denominator would get you down to. So you could have some that wouldn't pass the other test, the thing of a sub n plus 1 being less than or equal to a sub n. Wouldn't happen often, but it could. Okay? So, if it converges absolutely, it's got to converge when it's alternating. Because if they are, in general, getting smaller, and it converges absolutely, if all these were positive, then when every now and then you have some negatives in there, that's bringing the sum converging even faster. Okay? And that's the whole purpose of this. By direct comparison, you have the absolute value of sine is less than or equal to 1, always. Okay? And the n squared is always positive, so this thing is always going to be less than or equal to that thing. Okay? Because sine n is always between plus or minus 1, and most of the time it's going to be less than 1. So that will always work. It does converge, and by direct comparison test, the series, that one has to converge as well. Now, that's the absolute value. So this is what I would say. If the series absolute value of a sub n converges, then for certain the series summation of a sub n converges. Now, if a sub n is always positive, that will be the same as this. Okay, so this converges that. But if occasionally you have an a sub n that's negative, but the positive that would converge, then it just converges even more quickly. All right. Double the class size. All right. We're just going over these that are not going to be on your test, but trying to go quickly. I'm not moving very fast at all. Okay, I apologize for the board. I've tried to erase it more, and it just smears badly, so I got it. I think what my work study does, I don't know this for sure, but I think she comes in and puts way too much Windex on the board so it dries with the film on it, and when you try to erase it, it just messes. But she's not here today, so she can't clean it. I might be able to, but I'm not going to have any time to. Okay. So the converse of Theorem 9 is not true. Now, what's the converse of that? If this series converges, that doesn't guarantee the absolute value of it converges. The 1 over n. When you alternate the signs of that converge, the absolute value would not converge. Okay. And that's the one they use here. For instance, the alternating harmonic series, which would be that one, converges by the alternating series test, yet the harmonic series diverges, not alternating, but harmonic series diverges. And that type of convergence is called conditional. So a series could converge is absolutely convergent when that converges. Okay? But this thing could be conditionally convergent when only this converges, but not the absolute. Okay? So this obviously would have to be an alternate, well, have some negatives in it. It doesn't have to be alternating, but it has plus and minuses in it, but not necessarily alternating. If that converges, this series converges, is conditionally convergent when that converges. I mean, it looks like this is the same thing. I know they must mean something else. Oh yeah, I'm sorry. When the a sub n converges, if it does alternate signs somehow, or have different signs in it, but the absolute value doesn't converge, then this one said conditional conversion. Okay. Determine whether each of these series is convergent or divergent. Classify any convergent series as absolute or conditional. Just give me a gut feeling on this. Which of the do you think this is going to converge? at least up to here, this is 6 over 8, right? Well, what would the next term be?
4 over 16.
It would be 4 factorial, which is 6 times 4 is 24 over 16. Whoops! Greater than 1. So the terms aren't even converging. Because factorial goes up faster than a power, okay? Than a exponential function. So, no, that one will not converge. This one, however, is alternating series, and every one of these, this one's less than that, this one's less than that, and this is going to 0. So if this one converges, you think it's absolute or conditional? Yeah, it is conditional. You're absolutely right. Because, remember your p-test for convergent, if the p is less than 1, that's the power of your n down here. This is n to the 1/2 power. That's less than 1, so that doesn't converge when you just have, when it's not alternating, but it does converge. Yes. Okay. So the first is alternating series, but it does not apply because the nth term, the limit of the nth term is not 0. By the nth term test for divergence, however, you can conclude that the series does diverge. I didn't know I used that term, but we did, I guess. The given series shown to be convergent by the alternating series test, because we looked at both of those features. Moreover, because the p series diverges, the absolute value one, that makes it conditionally convergent. All right. And the last subtopic in this section is rearrangement of a series. Okay? Here's a finite sum. 1 plus 3 minus 2 plus 5 minus 4. Looks to be something rather strange, but it looks like the positive numbers are odd and increasing, and the negative numbers are even but increasing. Okay? Of course, this is a finite sum, by the way. It has a limit. It's not going to be. So, of course, it converges. It has a value. Okay? This is not necessarily true for an infinite series. Okay? Depends on whether the series is absolutely convergent or conditionally convergent. Okay? So you could change this to be 1 minus 2 plus 3 minus 4 plus 5. For just a finite, that's fine. Okay? If a series is absolutely convergent, then its terms can be rearranged in any order without changing the sum. If it's absolutely convergent, it's going to converge, no matter what, If a series is conditionally convergent, then its terms can be arranged to give a different sum. Now, they aren't necessarily going to prove that, but at least they're stating it. I don't think they're going to give a proof of it. Okay? And example 8 is an example of it. Alternating harmonic series converges to log 2 by rearranging the terms of the series, rearrange the terms of the series to produce a different sum. So, goodness gracious, what do they mean by that? Let's just let them describe it. Consider this. Let's do all the this is strange. This is 2 and 4. 4 is twice 2. I don't know what the pattern is on that. These two seem to make a little bit of sense. Then this one doesn't make any sense at all, especially when involving like that. Though this one makes the same sense that these do. Okay? That one just stuck out there by itself. This one doesn't make sense just like this one, but these two make sense. So, okay. And that's exactly okay, sorry. They grouped the first two and then having the negative 1/4. Okay. So I was seeing the grouping, but I was ignoring the 1 and doing the second. Okay. Now that would be 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 and so on and so on. And this is an alternating sequence, and it does have a certain pattern to it. Okay? What would be its sum? You could factor out a 1/2 from all those. That's certainly true. And then you have the alternating series of your harmonics, which is 1/2 of log 2. So here we had one that was log 2, and just by rearranging the order, you get 1/2 of log 2. That does seem totally bizarre, okay? But that's so freakish, I wouldn't worry about it. So we're not. You don't have to do any homework exercises here because you're not responsible for this. And I must have written something. All right. So let's move on to 9.6. Just wanted to show you some of these because some of these may pop up somewhere in your future. And if they do, I don't want you to be, oh no, this has happened before, hasn't it? We may skip 9.6. It's the ratio to, oh no, there it is. So let's see if we can go from current slide. Oh, now it's messing up. It looked good to begin with, now it's not. Oh, here it goes. 9.6 is ratio and root test. Looking okay to me. Use the ratio test to determine whether the series converges or diverges. Use the root test to determine whether the series converges or diverges. Review the test for convergence and divergence of infinite series. First, the ratio test. Test for convergence ratio test. Summation of A sub n be a series with non-zero terms. So none of these terms can be zero. Okay? The series summation of A sub n converges absolutely, okay, when the limit as n goes to infinity of A sub n 1 over A sub n is less than 1. You see, you could have let's see if I'm going to say this right. One of these, a sequence, that's what you're dealing with here, a sequence that it may be decreasing, but the ratio of them is still 1. The ratio of those is still 1, even though it's decreasing. For instance, 1/2. Anyway, as long as that ratio is less than 1. can't be 1. If it's 1, you don't know for sure. The sequence a sub n diverges when the limit is n goes to infinity of a sub n plus 1 over a sub n, absolute value is greater than 1. Okay? Or when the limit of that is infinity. Well, isn't that greater than 1? I mean, why don't we just leave it like that, greater than 1? Okay? Now, here's the problem. The ratio test is inconclusive when the limit of the ratio is exactly equal to 1. Some of those may work, some may not. Okay? If it's less than 1, converges absolutely. When the ratio, absolute value of the ratio is greater than 1, it diverges. No question. Okay? The ratio test is inconclusive when that ratio is exactly equal to 1. All right. Now, the convergence or divergence of this, if you get high enough in low numbers, it won't necessarily work. Like n equal 1, that would be 2 over 1. Okay? N equal 2, that would be 4 over 2. N equal 3, that would be 8 over 6. Okay? But after a while, like 16 over 24, yeah, now you've gotten so the ratio for large numbers, when n is approaching 0, is less than 1, that will converge. And again, factorials always beat powers, okay? Always, okay? Given time, get them big enough. Because a sub n is 2 over n factorial, you can write the ratios this way. 2 you have here 2 to the n plus 1 over n plus 1 factorial. And down here you have 2 to the n over n factorial. They just rewrote it this way as a division here. Well, that division, flip it and multiply it. And what do you get? The 2 to the n will go into 2 to the n plus 1 2 times exactly. The n will go into n factorial will go into n plus 1 factorial, n plus 1 exactly. Okay? So you have a ratio of 2 over n plus 1. If n plus 1 is going to infinity, that's going to 0. Okay? That ratio is definitely less than 1. Okay? It's no question. Okay? That's going to 0. And that's less than 1. Okay? That series converges absolutely because the limit is that. Oh, 10 o'clock scholar. Good deal. Welcome. Dawson's here. Increase the class size by 50%. Good deal. All right. So that converges absolutely. Okay? Because that ratio is less than 1. Absolute value ratio is less than 1. That's the only example they showed. Thank you so much. Okay. The next one, I bet, gave one that did and one that didn't, or one that was inconclusive. So, if you're interested, go to do the other examples. Okay? No, the second one probably gives one that does and one that doesn't. The third one gives one that you can't tell. And that, by the way, is found at larsoncalculus.com. You can see that and have them explain it to you. Now let's move to the root test. We're in 9.6, which is just what I've given you a slideshow of it in case you ever need it again. At least you've seen it once, okay? You're not responsible for this on the test. Here's this. The slides found some sort of corruption in them. Here's a place where it's corrupt. You can't see it. I'll tell you what it says. If you got a book, you can read it. Next test for convergence states of the series works especially well for series involving nth powers. Okay? So the series of summation a sub n converges absolutely when the limit as n approaches infinity of the nth power of a sub n is less than 1. Okay? That's the power test. Yeah. And in general, this is true. If you got something, now remember, if the series involves powers. So if the series got powers involved with it, like the nth power, n plus 1 power, n minus 2 power, something like that, usually the thing itself, raised to the power, is going to be increasing greatly. When you take the root of it, if you think about one over n, it diverges anyway. We knew that. But 1 over the square root of n diverges even worse because n goes like this, square root of n goes like that. So it's always less. So 1 over that would always be greater. So if the greater converges, if that limit is less than 1, then this will converge. Not just converge, but converge absolutely. Now, the series a sub n diverges when the limit as n goes to infinity of the nth root of the absolute value of a sub n. Of course, you have to have absolute values in there because even roots won't work if that's a negative number. But the nth root of the absolute value of the nth term there is greater than 1. Okay? If that is greater than 1, or infinity, which to me that's redundant. I mean, if it's infinity, it's greater than 1. So I don't know why they put that in there. Then that diverges for sure. But I think you can guess what the next line is. The root test is inconclusive when the limit as n approaches infinity of the nth root of the absolute value of a sub n is equal to 1. Just like it was for the ratio test. If that's equal to 1, you can't tell. Okay? So let's determine the convergence or divergence of this one. Now, surely you can kind of tell there's roots involved with that. But I sure don't want to try to figure out what that's doing too quickly. That is a mess. So let's see what happens if we take the square root of that. No, the nth root of that. So let me see if I can get, I wasn't going to do this. Oh, I can't write on these, sorry. Well, I'm not going to write anyway. We'll see what they do. They take the nth root of that, okay? And the nth root of e to the 2n is e squared, right? The nth root of that would be e squared. The nth root of this would be n. So what's that ratio? E squared over n, as n is going to infinity, that is going to be something considerably less than 1. It's going to 0. Okay? So therefore, that will converge absolutely. Apply the nth root test to it, and you do that, you get e squared over n, and when you do that, let n goes to infinity, e squares get left in the dust. Okay? It goes to 0, which is certainly less than 1. All right. Because the limit is less than 1, you can conclude the series converges absolutely and therefore converges. Now, next they talk about strategies for testing series. If you're having to do these, this is not a bad procedure to follow, sort of an algorithm. You'll study various tests for determining convergence and divergence of definite series. Below is a set of guidelines for choosing the appropriate test. Okay? Does the nth term approach 0? Okay? If it does, that doesn't tell you anything for certain, but if it's not, it's divergent. I mean, if the nth term is anything other than 0, there's no way that series is going to converge. So, first out, does the nth term approach 0? If it does, you don't know if it converges or not, but if it doesn't, it diverges. Throw it out. So, next, is a series one of the special types? Geometric, P-series, telescopic series, or alternating series? If it's a geometric series, yeah, you know what it converges to. If it's a P-series, you have a good test there of whether it converges or not. If it's a telescoping series, yep, I think that's always guaranteed to converge. An alternating series, you have a good test for it. Can the integral test, okay, now that was much earlier, I'm just change the series to an integral. The root test or the ratio test be applied? And if so, which would be the better one? Can the series be compared favorably to one of the special types like those? And if it can be, then you can probably determine. Okay? Whoa, we're not going to do these, but let's at least take a look at them. What do you think? Do you think this is going to converge? Let's forget about this for a minute and just do the sequence. Does that converge? It does. To what? Not to 0. Divide everything by n. And this will be 1 plus 0 over 3 plus 0. That sequence goes to 1/3. Hey, if the sequence doesn't go to 0, the summation cannot possibly converge. That's the very first thing they told you to deal with. Okay? Now, look. How about this one? The series summation of n equal 1 to infinity of pi 6 to the nth. It's just a number raised to the nth power. Okay? But it's a number. Pi is a little bit more than 3. 6 is 6. Okay? So this is going to be a little bit more than 1/2. And 1/2 to the nth power. You could compare it to that. No, maybe not.
It'll always be less than 1.
It's always less than 1.
So it converges.
Yeah, the ratio is less than 1. So yeah, that's what we'll do. The first one, the nth term test, diverges, like we said. This one, the series is geometric. Moreover, because the ratio is pi 6, less than 1 in absolute value, you can conclude it diverges. You're absolutely right. The third one, just let's go through these more quickly. Okay, we almost have to see the thing. N e to the minus n squared, okay? Because that looks just like a function. Just change the n's to x's, and that is a function that can easily be integrated. Nice. U substitution will work like a charm. You can use the integral test to conclude it does converge. The nth term of that series, I guess we can't. This is going to take a long time. That one, the nth term is going to 0, whereas this one, it was going to 1/3. So at least that indicates you have some hope here for that. But compare this to 1/3n. That one does converge, okay? No, wait. It's 1/3. I would say the nth term of the series can be compared to the nth term of the harmonic series, and after using the limit comparison test, you can conclude it diverges because the harmonic series diverges. Okay? And the rest of them, if you got your text, the summary of tests for series, that's, there they are. Knock yourself out, okay? There's lots of things you can go. We did the nth term geometric telescoping in P. We didn't do the rest of them technically. I mean, I reviewed them with you, but those are just some of the tests you can do. Oh, the second one does okay. Second half of the page does all right. And that just tells you you're testing the series, conditions for convergence, conditions for divergence, and then commentary. That's what those columns do. The test, the series, condition for convergence, condition for divergence, and any comment they have. Have finished 9.6. Again, you're not responsible for this on the test, but if you ever need it, I want you to at least have been exposed to it. All right, 9.7. This is what the main reason we're doing this, okay? I want you to at least know what someone's talking about when they say a Taylor polynomial, okay? And this is going to lead to approximations, okay? The objective here is to find polynomial approximation of elementary functions and compare them with the elementary function. To find polynomial approximations of the elementary functions and then compare them to the elementary functions. Okay. Then we'll find Taylor and Maclaurin polynomial approximations for elementary functions, and we'll use the remainder of a Taylor polynomial. I won't say how we'll use it, but they'll use it. So let's start with polynomial expressions or approximations of elementary functions. To find the polynomial function P that approximates another function F, begin by choosing a number C somewhere in the domain of F at which F and P have the same value. In other words, P of C is equal to F of C. Okay. Now, this is a little vague to begin with, but hang with it. The graphs of P of F pass through that point, C, F of C, and C, P of C. Okay, same point. The approximating polynomial is said to be expanded about C or centered at C. And what you're doing, let's say you have a sine curve. You get a polynomial that at this value crosses there. And then what polynomial function can you have that at least around C is very close to being the same as that sine curve? You can use any curve, I'll just pick up sine. Okay, geometrically the requirements that P of C is equal to F of C means that the graph of P passes through the point F, C, F of C. Exactly what we said here. Of course, there are many polynomials whose graphs pass through the point C, F of C. Okay? A whole bunch of them. Your task, should you choose it, okay, is to find secretary of this your task is to find the polynomial whose graph resembles the graph of F near that point. That's what I was talking about. One way to do this is to impose the additional requirement that the slope of the polynomial function be the same as the slope of F at F C, C F of C. So therefore, not only is P of C equal to F of C, P prime of C is equal to L prime of C. Okay? I haven't said it yet, but they're bound to in a minute. With these two requirements, you can obtain a simple linear approximation of F as shown here. Okay? Here it shows. P of C is equal to alpha C. That was the first requirement. Now that P prime equal F prime, that means this polynomial is a linear polynomial. Passes through there. Don't know where else it passes. It passes through there, and it has the same slope. Now look at this. For a lot of points close to C, those are almost identical. They do deviate, but ever so slightly. Okay? Near C, alpha C, the graph of P can be used to approximate, and this is a very simple polynomial function here, the graph of. Now, whatever function that is. Okay? So that's a first, you might say first order approximation. Now, we're not going to do it. Let's just go through it quickly. For the function alpha x equal e to the x, find a first degree polynomial function. P1 of x is a0 plus a1 of x, whose value and slope agree with the value of slope at x equals 0. So x equals 0, what's f of x? Alpha 0. E to the 0. 1. Okay. So you need a function that passes through 0, 1. Okay. I would say that your y-intercept be 1. That will work on it. Okay. Now what's the derivative of f of x at alpha of x, which is e to the x, at x equals 0? What's the derivative of e to the x? E to the x. And what's this value there?
Still 1.
Still 1. Okay? So its slope is 1, and the y-intercept is 1. That looks like to be 1 plus x. Okay? Whose value and slope agree with the value and slope of alpha x equals 0. Because alpha of x equals e to the x, alpha prime is e to the x, value and slope of alpha, the value and the slope of alpha x equals 0 is 1. Okay? So conclude that because P1 of x equal a sub 0 plus a1 of x, you can use the condition that P1 of 0 is equal alpha 0, show that a0 has to be 1, and then because P prime of x has to is equal to a1, you can use the condition that P prime be f prime, so that has to be 1. So there's the line. The polynomial 1 plus 1 over x. And this is what the exponential function looks like at 1, and sure enough, that's the line p of x equals 1 plus x. And again, for points really close, so awfully close, within what, about 0.4 or so, those are really, really, really close approximations. Okay. Now, a lot of sort of blah, blah, blah on that. Now, Brooke Taylor, I don't think I've ever seen any picture of him but this one. And this comes from a time far past. To me, it looks like he's in a bathrobe. And I thought, why would anyone pose for a picture in a bathrobe, you know? But it's not. This is how they dressed back then. Now, why he has his hair, it looks like he just came out of the shower. He has his hair all done up in a towel and he's in a bathrobe. I don't know. It just seems bizarre. And it seems like that's the only picture I ever see of him. But anyway, potential paper topic for any who haven't turned in a paper yet, which, by the way, is everyone but one has not turned in a paper yet. Okay? Just a little hint. And by the way, test 1, I've barely got half of the class in for test 1. And test 2, I don't see any test 2s in. And we're running out of term, folks, yeah.
When's test 3 coming out?
I'm sorry?
When's test 3?
We're going to get, that's the final exam.
Okay.
I'll be giving it to you next 2 weeks from today, the Wednesday after Thanksgiving. I'll be giving it to you, and it has to be back the next week. That's final exam week, which means you have 1 week to work at that one, and some people haven't even finished test 1. Please get test 1 and 2 done before you have the final in hand. Get your research paper done before you have that final, and you have just 1 week to do it. Please get those in. You got Thanksgiving week to work on them. Please work on them. Okay. Later we'll have a guy named McLaurin too. We'll see him later. For expansions about an arbitrary value of C, it is convenient to write the polynomial of the form Pn of x. Now this is the nth order polynomial. That's what the n stands for. That's how much you're going to get. And here you'll have a sub 0 plus a1 x minus c, because you're centering on that value c, plus a2 times x minus c squared, plus a3 times x minus c cubed, plus dot 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 up to a sub n of x minus 3 c to the n. In this form, repeated differentiation produces the P1 is going to look a1, because this is to the first power. You'll have 2 times a2 to that to the first power, 3 times a3 times that to the second power, and so on until you have n times. Now here's another one of the strange places they just throw in a vertical line. It's not in your text. It's not in the series. It's just on the slide. Sometimes they show up. So it's not there. You have to pretend it's not there. N times a sub n times e to the n minus 1. If you were to take a second derivative of this, now you just have your 2a2 plus 6a3 times n minus c to the first power, and then you have n times n minus 1 times a to the n x minus c to the n minus 2. And then the third derivative would then just be this coefficient, 6a3, and you keep going on down. The next term would have been a 3 times 4, a4 times x minus c to the n minus 2, or n minus 3, sorry. And the nth one would be n times n minus 1 times n minus 2 times a sub n times x minus c to the n minus 3. Keep on going, and finally on the nth one, this is all you can do, because now you're down to a constant. You have n times n minus 1 times n minus 2, all the way down to n2 times 1 times a sub n. Okay. That would be as far as you can take the derivatives, because it's a polynomial of that power. So you can only take n derivatives. Okay. Now, letting x equal c, okay, which seems like a strange thing to do, but then that makes everything 0, all right? X equals c, then all your terms up here that have an x minus c on goes away. So now this polynomial is just a sub 1, this is just 2a sub 2, 6a sub 3, 3 factorial times a sub 3, and so on. This is now n factorial times a sub n. Okay? So that's what those would have been. Exactly what I said. A sub 0, a sub 1 times 1, okay? A sub 2 times a sub 2, n prime, n factorial times a sub n. I wish they'd have put a few more terms there. Because the values of f and its first n derivatives must agree with the values of p sub n and its first n derivatives at x equals c, then what you have is that p of c must be f of c, so that has to be a0. F prime of c must be p prime of c, so that must be a sub 1, and so on. So these, It's not entirely obvious how they got this, except remember this is 2 factorial, that is 1 factorial, that is 0 factorial. Is your coefficient 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 3, that is 6, 4, okay, and n factorial is n factorial. So what they're doing is dividing the derivatives by the coefficients up there. They just listed them as 1 and 2, but they're actually 1 factorial and 2 factorial. So that last one is L sub n divided by n factorial would then be A sub n. They sort of pulled this trick on you there, without telling you exactly how, but why. But anyway, with these coefficients, you can obtain the following definition of what we call a Taylor polynomial, named after the English mathematician Brooke Taylor, and later the Maclaurin polynomials, named after a Scottish mathematician who came along way after Taylor. Well, not way. Maclaurin was 13 years, no, let me see. No, they were long about the same time. He's 13 years younger than Taylor, okay? So they did live a fair amount of time overlapping. I assume they probably worked together some, Britain and Scotland, not that far apart. Okay, but this is Cole and Maclaurin. Now maybe they worked completely independently and came up with these things. Okay, so here's the definition of the nth Taylor polynomial and the nth Maclaurin polynomial. Okay, of course the function n, f, must have n derivatives at some value c. Then the polynomial p sub n of x, this is polynomial degree n of x, is L sub c, that's at a0, remember, plus a 1 times x minus c, plus a2 over 2 factorial, f double prime, that was your a2, okay, over 2 factorial x minus c squared, and on and on and on. F, the nth derivative of f divided by n factorial, evaluated at c times x minus c, raised to the nth power. Such a messy board. That's the nth Taylor polynomial of f at c. Now, I wish they had broken this off. If c was 0, then they give this even a new name. P sub n is f of 0 plus f prime of 0 times x plus, because c is 0, plus f double prime of 0 divided by 2 factorial x squared, because c is 0. F cubed, okay, you have that. That's the nth, or we call it nth order, of the nth Maclaurin polynomial for F. Taylor's centered at some arbitrary value c out there. Maclaurin always centered at 0. It does make it simpler in the fact you just have powers of x, not powers of x minus c. And you evaluate at the same point, at 0. Okay. So we don't have really time to do this, but this is pretty nifty. Okay. Now, if you see an x in here, you know this is a, oh no, this is the Maclaurin polynomial. So don't have any c's in here. 1 plus x plus, because the derivative of all the derivatives of e to the x are e to the x, okay? And they're all, at 0, they're all 1, right? E to the 0 is 1. So all those are 1. So all of your numerators there for the Maclaurin polynomial are 1, okay? So this is what you have. 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, and so on. Now, I don't know how you first define an exponent, the number e, right? And by the way, when x is equal to 0, that's exactly 1. When x is equal to 1, so x equal 1, that would then be f at 1, that would be e to the 1. Okay, so let's do that. E to the 1. You know what that is. You can punch it in your calculator. 2.71, blah, 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 blah. Do it. See what you get. Yeah, e to the 1. Shouldn't be taking too much time. Say it. Wait. E to the 1 is equal to
2.71828.
3 what?
No, 718.
Oh, 718.
28. 1828.
Is that where yours stops? Okay. I guarantee you that pattern doesn't continue. Does yours go any further? Okay, well, it doesn't continue. Okay, so we're going to do P sub n of 1. So it'd be 1 plus 1, that would be 2 so far, plus plus 1/2, that's 2.5, plus 1/6, do that. Two 2.5 plus 1/6. Plus 1 over 24, right? Didn't you tell me that was 50/40? Yeah. Hey, look at that. With just 1, 2, 3, 4, 5, 6, 7 terms, we've got 1, 2, 3, 4, 5 digits of precision almost. Pretty close to that. And you could do plus 1 over. It's going to converge, and it converges really rather quickly. Okay? Now, when you did your calculator and did e to the 1, did they have that stored in there somewhere? No, it did a Taylor series. That's how it did it. It just did it really quickly. That's exactly what it did. This is easily programmable. Okay?
So the Taylor series kind of is the proof for e to the 1?
It's what?
It's like a proof for e to the 1?
No, it's just an approximation. Okay? And what your calculator does, it keeps it just ups it by 1. It keeps doing the same thing I was doing there mentally in my head, but it's doing it really quickly and just keeps going. But then when one sum differs from the next sum by less than some prearranged thing, and that would be some digit beyond what your calculator can show, it stops, because anything else is going to change the digit way out here. You only display this many, so why would it keep going? That's a really rough rendition of what your calculator is. That's what it is. Because otherwise you have to store all these things in a table. And it's not going to do that. It's going to do exactly what we just said. Okay. So any function that has n derivatives can do this. All right. Anyway, I shouldn't have wasted that much time, but I wanted you to see, because we knew those factorials already. Whoa. That's all they did. Example 3 is given by that. Okay, yeah, I see now. I was thinking they were going to do something else, but that's all they did. So what's the remainder of a Taylor polynomial? An approximation technique is of little value without some idea of its accuracy. So to measure the accuracy of approximating a function value f of x by the Taylor polynomial, Pn of x, you can use the concept of remainder, Rn of x, as defined this way. F of x is equal to Pn of x plus whatever the difference is between those two. The exact value, the approximate value, your error value. That's what I would call it, but okay. I guess that's a negative. So Rn of x is alpha of x minus Pn of x. The absolute value of Rn of x is called the error, okay, associated with the approximation. Okay? You use absolute value because you don't really care if it's higher or lower, you just want to know what it is. The next theorem gives a general procedure for estimating the remainder associated with the Taylor polynomial. It's an important theorem called Taylor's theorem, and the remainder given in the theorem is called the Lagrange form of the remainder. That's another name, another potential paper topic, hint, hint. Okay. Here's Taylor's theorem. If a function f is differentiable through order n plus 1, okay, on an interval I containing the number c. Remember, Taylor allows you to center at c. Then for each x in that interval I that contains that number c, there exists a z between x and c such that, oh man, okay, your f of x would be f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared plus f triple prime of c over 3 factorial plus f to the nth derivative that has n plus 1, nth derivative, evaluated at c over n factorial times x minus c to the n, plus your remainder. That's whatever the difference between the Taylor polynomial and the function is. That's your remainder. What is this remainder? It's the n plus first derivative. That's why you require the n plus first derivative at some value z that's in between your x and c. C where you evaluated the x where you're approximating. Okay? Divided by n plus 1 factorial. That would have been the next term plus times c, x minus c to the n minus 1. That's this with a c in it would have been your next term of your Taylor polynomial. So you say the remainder would be there's some number in between your x and c such that that's going to be exactly that remainder. We don't know what the z is, but it's somewhere in that. Right? Okay. That seems sort of foggy at best, but that's what it's called. Now, example 8, the third Maclaurin polynomial for sine x is x minus x cubed over 3 factorial. Remember, Maclaurin series always is centered at 0. So your sine of 0 is 0. So that one's out of there. Okay. And the cosine is your derivative of sine, and at 0 that's 1. So that's why your coefficient is 1. And then the derivative of cosine is minus sine, and again at 0 that's 0. So that's why you're skipping the even number terms, because those are all zeros, because sine of 0 is 0. But you have your odd number terms, but that because cosine of 0 is 1, but every other cosine is a plus or a minus. So that's why it's an alternating series here. So here's the third Maclaurin polynomial for sine x. Is P3 of x is x minus x cubed over 3 factorial. It says use Taylor's theorem to approximate sine of 0.1 by p of p3 of 0.1 and determine the accuracy. Rather than try to talk the way through it, let's just watch them do it. Using Taylor's theorem, which says that, now Taylor's theorem applies to Maclaurin series. Don't get that confused. It didn't say use Taylor's polynomial. I started to say, why would you do that? But then I realized it's Taylor's theorem. Okay, so it would be those first two terms plus that third term, the remainder term. And that would be the fourth derivative at z, 4 factorial, x to the fourth, where z is some value between 0 and 0.1. Okay, now that is sort of mushy there. Of course, if z is 0, and it can't be 0 because it has to be greater than that, that would have been a 0. So it's going to be the greatest here at 0.1, or near 0.1. So that's what I would plug in there, and give your approximation of the error. Since sine of 0.1 is approximately that, which is 0.099833. Punch in and see what sine of 0.1 is in your calculator. This is approximate. Give me the exact. Be sure you're in radian mode, folks. 3 what?
3.4.
Man, that's pretty close, wouldn't you say? Okay? Very close. And of course, it keeps on going. Because your error is the fourth derivative there, and that fourth derivative is sine z, follows that the error, the absolute value of r, seems like that should be R4, not R3, but okay. Oh, no, the error R3 can be bounded by this. Okay. What they're saying here is the sine has to be something between -1 and 1. So the maximum it could be was 1. So just take this thing and raise it to the fourth power and divide it by 4 factorial. And you're going to get a very small number, 0.0001 divided by 24. And that's 0.000004. And we were 1, 2, 3, this 0 corresponds to 0, 0 to 8, 9, 0 to 9, 0 to 8. Yeah, you're up there, and we were well within that. Okay, we were 0.00001. So certainly it's less than that. That's pretty good, though. Within 1, 2, 3, 4, 5 degrees of precision, 5 decimal places. That's incredible. And that's what you calculate. When you say your calculator, give me the sine of 0.1, that's exactly what it did. It just did 2 Taylor, maybe 3 Taylor polynomial. The next one, Maclaurin, maybe a little bit, maybe the next one. It didn't take it long at all to do that. That implies that, boy, they can beat you to death with this thing. So the sine of that is within 0.009833 and 0.009837, and we found it was 3.4. Okay, with some change. All right. I know this is too fast for it to make a lot of sense, but you need to have been exposed to Taylor and Maclaurin series, polynomials. Series are coming up later. How are we doing on time? 9 minutes? Okay. So let's move on to 9.8. I'm taking too long on this. I'm sorry. We need to get into 10. Oh, this is another one. That just means I can't write on these, so you'll have to just follow in the book. Okay? Okay, chapter 9 is still infinite series. 9.8 is power series. Okay? Objectives here are to understand the definition of a power series, to find the radius and interval of convergence of a power series. What do we mean by the radius of the power series? We'll see. Determine the endpoint convergence of a power series, and differentiate and integrate the power series. Well, that we can do, I think. Let's see. An important function, f of x equal e to the x, can be represented exactly by an infinite series called the power series. It's actually a Maclaurin series, okay? For example, the power series, our representation for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x 4 over 4 factorial, all the way up to x to the 4th over 4 factorial. I mean, x to the n over n factorial. For each real number x, it can be shown that the infinite series on the right converges to the number e to the x. For incredibly large x's, it may take a while, but it'll still get there. Okay? Definition of the power series. If x is a variable, then the infinite series of the form summation of n equals 0 to infinity. They start this one at 0 usually. A sub n, which would be your a sub 0, here was your 1, times x to the 0, in this case it was 1, okay? And this actually doing exactly what I was saying here. A sub 0 plus a1 times x plus a2 times x squared plus a3 times x cubed plus together. On like this. That is a power series. Or generally an infinite series of the form. All this looks the same. But now we're going to do an x minus c. So this was pretty much Maclaurin, this is pretty much Taylor, seemingly looking like this. Okay? And that would be a sub 0 plus a sub 1 to that to the first a to the okay. Looks an awful lot like a Taylor series, doesn't it? That's also a power series centered at C, where C is a constant. All right. And this is just the Taylor series. You don't need to know that, but it is the Taylor series for e to the x. Okay? That's the power series centered at 0. That is what we were just using. Okay? Now, here is a power series centered at x at -1, which would be x plus, wait. Have they got that right? No. Oh. This is where the glitch is. Okay? I can't write it in because I try to activate a pen because this one's been, see, I don't have any control of the pen. So, oh. This one would be just like this, except everywhere you see a minus here, you put a plus. Okay. I can't write it. I mean, I could write it on the board. If I had a decent marker, I don't think I do. No, I'm sorry, there's one difference here. The one they list here has a -1 to the n in front, and then pluses everywhere. This one has a 1 over N in front, which is not the same thing, okay? They're just listing some power series. That's all they're doing, okay? Okay. Now, we don't have much time at all. Radius and interval of convergence. A power series in X can be viewed as a function of X, and that's how you can express it, where the domain of F is a set of all X's for which this power series does converge. Of course, every power series converges at its center of C, because the F of C is equal to that, okay? C minus C is 0, and that would be that, A0, okay? This is probably too fast, too furious to make too much sense, but so C always lies in the domain of F. And theorem 920, which is coming up, I don't think we'll get enough done. Let's stop here. We'll stop with radius and interval of convergence. Sorry, I'm taking too long on this. I didn't mean this to take so long. Power series are fine. I mean, but the next one that we'll do is a geometric power series, and you're introduced to Joseph Fourier, who had another famous series named after him. And then there's, Then in 910, we'll do Taylor and Maclaurin series. We've done the polynomials, now we'll do the series. And I think that's the last one. So hopefully I'll get through this. But boy, we only have, I don't know. Let's say we just jump to Taylor series next time. I won't continue it because this is taking too long to do them all. So next time we'll just jump to Taylor series. Taylor and Maclaurin series 910. The others are great, but we just don't have time. I want you to see these because these are important. And then the others are important too, but Taylor series is the culmination. Probably depends a little bit. What we'll do in 10 then, not going to do 10-1, but I'll try maybe to do a very quick PowerPoint of it. But then we'll do 10-2, 10-3, get as far as we can, and that will be what your test will cover. 10-2, 10-3, maybe 10-4. Hopefully 10-4, good buddy. Okay, so go from there. Sorry, not well planned.